In this video, we're going to look at a couple circuit analysis techniques that can be helpful if our circuit isn't quite in a form where we can use those general equations from a couple videos back. So electrical engineers, you should already be familiar with these techniques, so hopefully it's a little bit of a refresher. For mechanical engineers, you might or might not have seen these. So for anybody from both groups, if you want more details or want to see some more information, just let me know and I'll be happy to provide that. So the basic idea is, let's say we have a circuit that looks like this, and we run into an issue because we note that although this circuit looks really similar to the one from the previous example, over here on the left side we now have a voltage source. And if you go back and look at the general equation, you'll note that nowhere in that equation do we have a way to account for an applied voltage source. Now, of course, we could still use node voltage analysis on this circuit. Double E's, electrical engineers, you might be more comfortable just doing that. But let's say you're looking to just take an algorithmic approach. You don't really want to be thinking about the analysis. You just want to be thinking, I want to plug into the equation here, 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 and do that. In that case, what we want to do is we want to change this voltage source into a current source somehow. Because again, our equations don't account for voltage sources. And we're going to do that with a technique called source transformation. And so essentially what our source transformation allows us to do is to take a voltage source in series with a resistor, as we have here, and convert that to a current source in parallel with the same resistance. So if we want to do a source transformation for this circuit, let me just copy our circuit here, and then let's get rid of this momentarily. So what we're going to do then is we're going to replace this highlighted part with a current source, which is going to be in parallel with that same resistance. So here we have Rx, so again that resistance value is the same, and here we have a current I. Now, of course we want to know the value of that current I, so again let me just sort of highlight that we've replaced this voltage source with this current source in parallel with that resistor. So our big question then is, what is the value of that current source I? Well, we can just do Ohm's law to figure that out. So we know that V equals IR, so rearranging, we could just say RI is equal to V over R. And of course, we could go either way. For the purpose of this class, of course, if we're trying to plug in another equation, we're only going to be going this way. But we could also go in the other direction and convert a current source in parallel with a resistor to a voltage source in series with the resistor. And the same idea applies to impedances, because remember, we treat impedances like resistors when we're working in our frequency domain. So that's the first technique I wanted to show you, source transformation. And again, if you want more details or to see examples with that, just let me know and I'll be happy to show you. The second thing that I want to consider here is, let's copy this circuit again. So let's say we're interested in our transfer function, and instead of just an inductor over here, maybe we have another element in series with it. So maybe we have a resistor and an inductor in this branch. So this is still SL2, let's call this R3. And let's say we're interested in some voltage here. So maybe this is voltage, let's call this voltage V sub Z. So let's say for our transfer function, we want to have, and let's say we have also transformed this so that we already have our current source. So we already have our current source, so we don't have to worry about doing that. So we're ready to just plug into our equation. But for our transfer function, it's specified as Vz over I. So our transfer function is Vz over I. So how do we get around that? Because if we do our node voltage, we're going to end up with something that looks like this. We're going to have a voltage V1 here still, and we're going to have a voltage V2. So of course, once we solve for V2, last time in our previous video, we said that that V2 was the same as our voltage Vc, which we were looking for, but now we want our voltage Vz. And so the way we can get around that is by using a technique called voltage division. And so before we look at voltage division, I just want to mention one thing really quick that I forgot about our source transformation. One thing to note is that the current direction is important. So the direction of this current source here is based on the polarity of our voltage source. So note that the current is going in a direction that would be through a voltage rise, so from negative polarity to positive polarity. So something important to keep in mind. Okay, so coming back to this idea of voltage division. So let's, instead of focusing on this circuit, let's look at a simple circuit first. So let's just say we have a voltage source and we have a lot of resistors in series. And so ultimately this would scale up to however many resistors you want. But the key thing is that these resistors need to be in series. And so I say resistors, but remember we treat impedances like resistors in the frequency domain. So we could also have any number of impedances in series. But let's look at a simple circuit with just resistors. So let's say we have a circuit with 4 resistors and some voltage source Vs. Well, if we're interested in, let's say, voltage V3, by definition, our voltage divider equation is going to say V3 is equal to the input voltage, which in this case is Vs, times some ratio. In the denominator of the ratio, we're going to have the sum of all the resistances in series. And so of course, remember, if we're in frequency domain, we can just replace that with impedances. So in this case, it's R1 plus R2 plus R3 plus R4. And then in the numerator, we have our resistor that corresponds to our voltage of interest. So in this case, that would be R3. So we get something that looks like this. Now, if we take that back to this example here, so let me move this down a little bit. So if we take that back to the example, of course, the biggest difference now is we're working with impedances and we don't necessarily have an explicit voltage source. And that's fine, because really we can have anything as our input voltage. In this case, we're talking about the voltage between these 2 points here. So if it helps, we could redraw the circuit and think of it as just some voltage V2, and then we have a resistor and an inductor in series, but again, we're talking about just impedances, so we have SL2 and R3. So if we're interested in this V sub Z voltage, from voltage division, we could say V sub Z is equal to our input voltage, V2, times some ratio. In the denominator, we have the sum of the impedances, so in this case, that's R3 plus SL2. And in the numerator, it's the impedance associated with our voltage of interest. So that would just be R3. And so that's how we would do voltage division. So again, with either of these techniques, let me know if you have any question or want to see more details. Hopefully you won't have to use them too often, but again, the main reason you would need to use them is if for some reason we have to slightly adjust our circuit so we can use our general equations, or maybe we have to do a little bit of extra analysis to help us get our transfer function based on our defined input and output.